right now the plan is test on Thursday. Okay, I got your study guide. I'll hand it out. Ready to go. We got a short lesson today, but it's really, really cool. We're at section 4.9. We're not even going to do 4.10. We're going to get in chapter 5 as soon as we can, where we add up the area of an infinite number of rectangles, and the whole world is perfect after that. So, okay, that's where we're at. All right. Yeah, I just change it all the time. So, all right. As soon as you feel bad for yourself that you got so much homework or something like that, your life could be worse. You could be Peyton Manning right now. Peyton Manning, that poor boy. Oh. Maybe hopefully he's not listening to this video right now. He might feel, we don't want him to feel bad. All right. Problem statement. Okay, so a couple statements. Newton's method, it's really cool how he does this. But you got to remember, so you're Isaac Newton. You're sitting back in the year 1680, and you're trying to work through some mathematical problems, and you realize that not everything is as nice as like x squared minus 3x plus 2, right? It's a nice quadratic equation. It's really simple to deal with, isn't it? And we can graph it. We can find the x-intercepts, the y-intercepts. We know it's symmetrical about the axis of symmetry. A lot of information you can tell about that. But what about other situations? For example, did you ever think about this? If somebody asked you to tell them what the square root of 2 was to 5 decimal places, accurate to 5 decimal places, and you couldn't use a calculator, how would you do it? Guess and check, okay? So this is a good idea. Like, what might be the first number you'd guess? 2.4, right? And that would be too high, so then you'd guess 2.2, and that would be too low, so you might average them and go 2.3. And then you might try to find upper bounds and lower bounds and average in between, and kind of, you kind of go like this, right? You end up, yeah, it's a really good idea, okay? Newton found a way to use calculus to do this incredibly quickly. And you got to remember, it wasn't just the square root of 2, because he didn't have a calculator. And so anytime, but they would keep charts. So, he would write down the square root of 2 and write it out to, 8 decimal places. Once he found it once, he could always look back at the chart. But if you ever needed to find a new one, well, that was concerning. So, here's what we're going to do. We are going to do the kind of the algebraic and the raw representation over here. And over here, we're actually going to do a problem. We're going to work it out. So, example, what is the square root of 5 to 4 decimal places, okay? And so here's what I'm going to do. Calculus always involves a picture. So I'm going to draw a picture. And I'm going to draw, this is going to be the graph, f of x is equal to x squared minus 5. Now, do you know why I picked the equation x squared minus 5? Very good. The x-intercept here is going to be the root of 5. See how I got that? Pretty simple. So, and now I'm going to use Emma's idea that I have a general guess. I know that what's the smallest integer that you would use to try to guess for the square root of 5? 2. And that would just be a silly guess, but it's still a guess. You know what I mean? Like if my daughter Kira said 2, I'd be like, oh, well, that's a good idea. For calculus 2, it's not so much, right? So we'll pick 2. Now, that's good. And then what's 3? And that's just silly. But we'll pick it anyway. It's somewhere between 2 and 3, right? Okay. So we are going to call our function simply f of x. Now, what we're going to do is we're going to make a guess, just like Emma said. And you guys are going to want to guess really close right away. I don't want you to try to guess really close right away. Let's just pick... no. Let's guess 3, okay? I'm going to guess 3. Because we're going to call the initial guess x sub 0. So x sub 1, x sub 0 is our initial guess, okay? Watch what we're going to do. Okay? This is super important. This is understanding Newton's method. Here's what Newton said. 3 is an easy guess. Okay? If you wanted to see if 3 was actually an answer, what would you do? You'd multiply it by itself. You do 3 squared. Okay? Or you could plug it into the function and see if you come up with the result of 0. In fact, you wouldn't get 0, would you? You get 4, right? So I'm going to represent that check right here, okay? If I plug in that guess of 3, I get an output of 4. I don't get 0 like I wanted to. But watch this. This is where it all comes clear. Is it easy to find that point? Yeah, it sure is. It's easy to find that point. In fact, okay, you told me that that point right there is the point 3, 4, right? Or if we were to represent that as a point on a line, that would be our initial guess, x sub 0, and then what would the y value be? F of x sub 0, yep. Okay, so that's our point on our line. Watch. What am I drawing? A tangent line. Look at this. Look at this. Look at, I'm trying to come up with this blue spot. Look at the x-intercept of my line. Is that close? Closer to the blue? Yeah, it's a lot closer, isn't it? So the whole idea is this. If I can find the x-intercept of that tangent line, that's a really, really good approximation. And if it's not good enough of an approximation, watch what I can do. I could take that value, plug it back in, see what the output is, do the new tangent line, how do you like that? How do you like that approximation? So you can see my first initial guess of 3, or x sub 0, we knew is not very good. But with just doing Newton's method by finding the x-intercept of the tangent line, we came out with an estimate really, really nice. Now, a line has degree what? What's the degree of a line? 1. It's degree 1, right? So when you solve for this, are you going to have any square roots? No. And so it's a great way to represent irrational numbers in really more of a rational approximation. And so that's what we're going to do. Now, in order to make this work, though, we need to find a slope so we can write the equation for the tangent line. Now, in this situation, let's just think about it, okay? Let's just think what we're doing. We know that the point is 3, 4, okay? How do I come up with the slope of that line? Take the derivative. What is the derivative? F prime of x is equal to 2x. So therefore, the slope is equal to what? No. 6. How did you get that? You plugged x sub 0, or your guess, into f prime of x. So here's what we have. If you want to know the slope, you take f prime of x sub 0. Now we're going to use Elizabeth method, and we're going to go y minus y1 equals m times x minus x1. The horror. Okay, here we go. We're going to work with the right side first, and then we'll do the algebraic representation a little bit. Okay, so now what we want to do is we want to write an equation for a line, but really what part of that line are we looking for? The x-intercept. The x-intercept occurs when y is equal to 0. So we can put 0 in for y. What goes in for y1? Minus 4 equals 6 times x is going to be the x-intercept that you're solving for, minus what's x sub 1? 3. So now we get negative 4 is equal to 6 times x minus 3. We divide by 6. Negative 2/3 equals x minus 3, and then we divided by 6. I'm sorry. For some reason, when I saw you pass Algebra 1, Algebra 2, and College Algebra, I was thinking I could divide by 6 without distributing. Just don't know what's going on. All right. They don't think I'm funny because they don't know enough math yet. All right. No, I'm good. Okay, so that we add the 3 over, and when you add 3 to both sides, you get 2 1/3 is equal to x. Now, take out your calculator, okay? Because you're looking for the x-intercept, and the x-intercept occurs when y is equal to 0. Okay, shh, boys and girls, watch again. We want to come up, right? But now the idea is we want to understand Newton's method. We really would need about 3 days to give it its full usage. But so we're going to kind of cut some corners here. If we do take 3 and we square it, you can see that you get 9 as opposed to 5. That's a really poor guess. But watch what happened when you pick 2.33. So we pick 2 1/3 and you square that. Look at how good the approximation is. All of a sudden you get 5.44. Well, that's a lot better, isn't it? That's significantly better. Okay. Well, but then we would just do it again. Okay. And that's the idea. And so we're going to do some example. What's that? Well, when the previous decimal doesn't change, for example, for this one right here, when we take 2.3 and we square it, we get, your next guess would be like 2.28 or something like that. So you saw that the 2 didn't change, but the 3 did. Okay, and so the idea is, Solveig, when you see that you get a new result where there's a decimal that hasn't changed, then you keep that and you realize that you just need to do it until you have, say, 6. It's accurate to 6 decimal places. So it all depends on how accurate you want to be. Now let's just finish this off so we can see the actual formula, because there's a quicker way of going about this. Okay. So let's write this out, and then we can be good to go. If we're solving for the x-intercept, what's the y value? 0. Minus. Over here, what is my y sub 1 value? F of x sub 0 equals, what's m? F prime of x sub 0 times x minus, what's x sub 1? What's the point on the line? X sub 0. So I'm going to do some tricky math again. Okay. All right. If I simply, so the 0 just goes away, I'm left with a negative f of x sub 0. I'm going to divide both sides by f prime. And so you get negative f of x sub 0 divided by f prime of x sub 0 is equal to x minus x sub 0. If you want to solve for x, that would be your x-intercept. You would just add x sub 0 to both sides. So your new guess is that x value, we'll call it x sub 1 now as my new guess, my new x-intercept, and that's equal to, if you add that over, you get x sub 0 minus f of x sub 0 divided by f prime of x sub 0. So this is your formula. I give that to you on the test. I give you a sheet on the front of the test where you got all the formulas that you need. But this is Newton's method. You understand, because of the picture that we drew, exactly what Newton's method is doing. You're closing in on a better guess. And it's a very efficient and effective manner by which we do it. So let's put it to work to do 2 problems on the back side. And this is what you're going to be asked to do on the test. It says use Newton's method to approximate the following to 4 decimal places. Okay? So we have to get it right to 4 decimal places. Okay? In order to do that, I'm going to write down Newton's method. Newton's method says, right at the top, x sub 1, my new guess, is equal to my initial guess minus f of x sub 0 divided by f prime of x sub 0. So, square root of 7, what do you want to guess? Okay, 2.5. We'll roll with it. So, x sub 0 is equal to 2.5. I need a function. X squared minus 7. Very good. So I need f prime of x is 2x. So, yes, you will use your calculator on this portion, but you can't, so I have to see your guesses. So like on the test, I can go back and check your guesses to see if they work out appropriately. And so here's all you have to do, okay? All we're going to do is take 2.5 and we're going to plug it in. 2.5 minus, what do I do at the top? F of, yep. So I've got 2.5 squared minus 7 then in the top. So parentheses, 2.5 squared minus 7 in the top. Divided by, what do I have in the bottom? 2 times 2.5. 2.65. So that's my new guess. So, are we correct to 1 decimal place yet? Not yet. Okay? Because it changed. So we got to try it again. Yep. Exactly. You got to list your function, you got to list your derivative, you got to list your guesses, and I have to be able to check them. Yep. Oh. Nope. You won't. 2.65 squared minus, well, I'm sorry, 2.65 minus, parentheses, 2.65 squared minus 7 divided by 2 times 2.65. Ooh. So how many decimal places should I write it to? 4. I can see if it changes. So we've got x sub 2 is equal to 2.6. So look at how closely we, how quickly we were able to generate something that was, accurate. Let's try this guess now. We'll try 2.6457. So 2.6457 minus, parentheses, 2.6457 squared minus 7 divided by 2 times 2.6457. I guess maybe I could round it up. So to answer Solvay's initial question, how many times do I have to do it? Well, here it looks like I had to do Newton's method once, twice in order to come up with we did it total 3 times to verify, but it looks like twice was close enough. Okay. Now let's see how close we are. What should we do with that value? If we square it, we want to come up with 7. Ooh, that's pretty close. Pretty close. Okay. Let's try cube root of 11. F of x is x cubed minus 11. F prime of x is I know that you guys were able to generate, but as you're doing it, you do understand why we get an answer that works out so quickly. As you look at the drawing, you can see why Newton's method is so efficient. Okay, it's all to do with the drawing. Okay, all right, let's do it. What's your guess? We're gonna let Megan guess. What do you want to guess, Megan? 2.2. Okay, we'll pick 2.2. Now, just make sure that the cubed root of 8 is what? 2. And the cubed root of 27 is, so you know it's going to be, what? So you know it's going to be, I'm practicing handwriting today later on. Okay. We know that we're going to be between 2 and 3, so Megan picks 2.2, we'll roll with it. X sub 0 equals 2.2. Let's do it. (2.2) minus parentheses 2.2 to the third minus 11 parentheses divided by 3 times 2.2 squared. Whoa. How many decimal places should I write it to? 2.2242. Well, would you expect anything different from Megan? Ooh. 2.2242 minus parentheses 2.2242 whoop. The third minus 11 divided by 3 times 2.2242 squared. 2.2240. Are we accurate to 4? We're not. So we need to do it again. That's what we got last time, wasn't it? 2.2239. Yep. So, well, last time I rounded to 4.0 and we had 3.9. It stayed 3.9 again, so we're good. I probably should have rounded it the first time. Yeah. I'm sorry. Looking at my method, you really shouldn't round till say the very. Well, yeah, you really don't need to round. Really don't need to round. Okay. It should stay the same. So. Okay. Last thing I want to show you guys. Cross these off. -2, -1, 0, 1, and 2. Let's plot those. Okay, so draw that approximate graph, and this is the last piece. And you guys, honestly, if we went to add some of those snow days, we definitely spend at least one more day on this. But just in the scope of what you need to learn for calculus, Newton's method is not, just an essential piece to your learning. So here's the deal. The question is, determine graphically what happens if Newton's method is used for the function whose graph is shown below. So picture Newton asking about the second question, or the first question, and that was, how do you find x-intercepts for things that you really don't know how to solve for? So you tell me when I get to the x-intercept. Yep. So just think, okay? Let's suppose that somebody guessed -2. Your question is, would they ever come up with the blue dot? Watch what happens. If you go ahead and do Newton's method, you would guess -2 to start off with, okay? You would then evaluate it, and then you would draw a tangent line, and after that you would find what? The x-intercept, which would be like way out here. As you continued to do that, what would your x values do? They would go to, they would go to -infinity. Well, that's problematic. We would like to use Newton's method to get the blue dot. We're seeing what happens if we do different guesses. What happens if you guess -1? It's gonna, same thing's gonna happen. You're gonna go to negative infinity. What happens if you guess 0? It's undefined. That would be a dumb guess. Well, no. If you've got, okay. Larissa asks a very, very, very good question. She asks, she says, how do we know if it's a bad guess unless we have the graph? First of all, if you have a graph of 1 over x, you know that 0 would be a bad number to pick, right? Because you know it's undefined there. But here's the answer, and this is what we would do if we had, a couple more days to spend on it. The answer lies in this. You have some interesting behavior here, don't you? Like, we could graph this right away. We could look at our concavity test, our increasing, decreasing test with the first and second derivative, and we could sketch most of this graph. You could find that you have a local min. You could find that you have a horizontal asymptote. We could find all that stuff that we did in Chapter 5. The one thing we couldn't find was that spot. So the answer to your question is, you don't know until you actually sketch a general graph and then zero in on finding the spot. So if Isaac Newton really had to work through this problem, he'd do all the calculus that we did in section 4.5 and sketch the graph to the best visibility, and he'd look at it and say, hey, -2 is a pretty bad guess. We got to guess something more like the number 1. Watch what happens here. What if we guess the number 1? Okay? We pick 1 and we evaluate it, and once we get that spot, we evaluate it, we do what? We draw a tangent line. Now here's the crazy piece. You can't really tell by the drawing, but hopefully my tangent line falls before 0. If it falls after 0, I'm in trouble, aren't I? So you can see how difficult that could be. Hopefully I fall before 0. I'll draw it like that. Now watch what happens here. So now I have a guess here. So then what would I do? Plug it in, and you would put it in, and you get some spot there, and then you draw a tangent line, and so it looks like it would, find it. It would get to that spot. It would find the blue dot. You would go to the answer, okay? It'd find where it was supposed to go. Well, look what happens if we guess 2. We plug in 2, and then we draw a tangent line, and it's going to cross somewhere up here. Yeah, it's going to go to positive infinity. So, at the end of the day, the question is, does guessing matter? It does. If you are guessing for these two, really doesn't matter a whole lot. I mean, you're going to be able to zero in on those pretty quickly, but that's because you have a reasonable guess. We need to have reasonable guesses. Even if you started with a guess of 100 here, that's a really bad guess, but you would eventually get back to where you need to be. Whereas in this situation, got to be very careful. Hannah? I just drew it. I just wanted to give you guys an example, okay? All right. There's your assignment, and I have your study guide. I'll hand it to you on the way out.